Okay guys, welcome to part B of our first PowerPoint that we've been going through in class. So what we're looking at here is we're looking at energy sources in particular. Now we're going to look at how does the body create movement for energy. So we've just looked at where the body gets energy from in terms of our food sources. Now we're going to look at how does it actually take that food energy and create movement. So just a thought, here's a good analogy. So the body is like a unique car. So imagine it that we've got 3 fuel tanks. The two things that determine which energy system we're going to be using for a particular exercise are the intensity of the exercise, but also the duration, so how long the exercise will be performed for. So these two things will decide which of these fuel tanks as such will be used the most. So the first system, imagine that we're entering a drag race. So the car needs a quick burst of speed. It only lasts 3 or 4 seconds for the race, but we need to go as fast as we can. Second type of system, or the second analogy, is a hard lap. So imagine that there's a Formula One race here, a qualifying race. You need to go as fast as you can for that one lap. So we need a high intensity effort, a high intensity of speed over a longer distance than the drag race, but sort of like a medium distance. So one lap of a Formula One track. The third type of a system, or the third example here, is a longer race. So imagine the Bathurst race, where it's an endurance event. The idea is that we still need an amount of speed, but the requirement goes, or the preference goes from using speed to being able to drive that car for a longer period of time. So what we're actually talking about here is we're talking about 3 systems our body uses to supply us energy. So we spoke about before, the food that we eat is broken down to form the body's energy molecule, which is what we call ATP. So ATP stands for adenosine triphosphate. So essentially what we've got here is we've got a adenosine molecule plus 3 phosphate molecules. Now these are all joined together, as you'll see in the next slide. So where we get our energy from is by breaking away of this last, or this third, phosphate bond. So all these bonds here are weak bonds. This bond here is a strong bond. So this last one, it wants to break off. So that breaking off of that third molecule is where we get energy, which you'll see in a minute. So this molecule, the good thing about ATP is it can be then resynthesized in order to be broken down again to create more energy. So like I said before, what we're seeing here is the last phosphate group in this adenosine triphosphate group breaking off, and this little explosion here is a releasing of high energy, a releasing of energy for all sorts of different things. So as a result, the phosphate breaks off, but like I said before, this is a reversible reaction, meaning that what we're left with here is an adenosine molecule plus 2 phosphate molecules. So the actual molecule now is what we're left with is called ADP, or adenosine diphosphate, plus another phosphate just sitting off the edge. So there's 3 ways in which we can resynthesize this ATP from ADP, and the first one is this way. So it's important to mention that this is a cycle, so it's a continuous cycle. As long as we get food energy to reconvert that phosphate back onto the ATP, this cycle can continue to happen. So what happens is, like we showed before, as this third phosphate breaks off from the ATP molecule, we get ADP. Phosphate molecule breaks off. Now that little energy release is what we use for muscular contraction, things like digestion and nerve transmission. So things we need energy for. Food energy, as long as we've got energy from carbs, fats and proteins as an extreme case, we can resynthesize that ADP back into the ATP. So more closely, we're looking at breaking down the 3 energy systems. There's 3 ways in which our body can provide us with energy. The first system we're going to look at is the ATP-CP, or the adenosine triphosphate creatine phosphate. You're going to see this referred to as a few different names. We're going to cover that in a minute. The second energy system is the lactic acid system, also known as the anaerobic glycolysis system. We'll talk about that in a minute. And the third energy system is the aerobic system, oxygen system, aerobic glycolysis, or even aerobic lipolysis, which we're going to cover in a minute. So the first system we're going to look at is the ATP-CP system. Other names you need to know or you need to be aware of are this system can be referred to as PC system, so creatine phosphate or phosphocreatine system. It doesn't matter, it's the same system, it's the same molecule. I like to say CP, sometimes I might say PC, it's up to you guys. We'll also refer to the system as the phosphate system, so it's to do with the breaking off of the last phosphates. That's what we refer to as a phosphate system. And alactacid system. So the word alactacid essentially means we're talking about anaerobic, we're talking about something that happens pretty quickly. That's all you need to know here. So what's happening in this system? The creatine phosphate is stored in our muscles ready to go. Inside our cells, creatine phosphate is there ready to go. So we use this system for short-term, immediate, intense or high-intense exercise movements. So usually things that only last between 0 and 10 seconds. Now the word anaerobic appears here. The word anaerobic means without oxygen. Good thing about this system is there are no waste or byproducts in this system. So here's another diagram of how ADP gets resynthesized back into ATP for this ATP-PC system. So here we've got the energy being released in the form of going towards muscular contraction, same as before. But now here we're getting our energy from our CP stores inside our muscle cells. So this system occurs 0 to 10 seconds. It's a very fast, high intensity, short duration movement. We need our energy to be coming from our CP stores. So these creatine phosphate stores are located inside the muscle cells. And that's essentially the limiting factor of this system. We can only use this system as long as we've got enough of these CP stores. So essentially what happens is the creatine piggybacks up onto the phosphate, grabs the phosphate molecule, helps put it back onto the ADP molecule to resynthesize ATP. So that's the importance of creatine phosphate in this system. So it's also important to know that once depleted, so once we've used this system up, CP can be resynthesized very quickly. So I said before there's a limiting factor of how many CP stores we've got in our muscle cells. You are limited to around about 10 seconds worth of those CP stores, but what's good is if you actually stop the exercise after 10 seconds and you completely rest, technically we can regenerate or restore 50% of these CP stores after 30 seconds of rest. Now it's important to know that it must be rest. We can't do an active recovery. Active recovery being where we're walking around or moving. So after approximately 3 minutes of rest, you'll see here that we can restore about 100% or close to 100% of these CP stores. So if you think about that in a real life situation, if we go outside and do a 30-meter sprint, or even a 50-meter sprint, something that lasts under 10 seconds, if we rested for 30 seconds, we're going to get 50% of our CP stores back. If we rest for 3 minutes after our 50, 80, 90-meter sprint, which lasts under 10 seconds, we're going to get 100% or nearly 100% of our CP stores back. So in terms of our performance for the next sprint, if we rest for 3 minutes, we're going to get pretty much close to what we performed or how we performed in that first sprint. Now there's some other factors that take into consideration why or why not you might not reach that performance level, but technically speaking, we've got enough CP stores to use this system again at 100% of intensity if we rest for 3 minutes. So the second system we're going to look at is the lactic acid system. I like to refer to it as the lactate system. It just seems to roll off the tongue a bit nicer. Other names we're going to refer to it as the lactacid system, so similarly to the ATP system without the A. So lactacid takes a bit longer. But the most important term that we're going to use is, or refer to the system as, the anaerobic glycolysis system. Now we went through this in class. The word anaerobic, what does that mean? Without oxygen. The word glycolysis, what does this mean? The word glycolysis means, if we break it down into glycogen, olysis or lysis, breaking down of. So glycolysis, breaking down of glycogen without oxygen. Okay? There it is. So the main energy system that we use in activities ranging from around 20 to 90 seconds. So what's happening between that 10-second period and the 20-second initiation of the lactate system? I'll leave you with that thought to a bit later on. So the problem with this system is that we produce this waste product called lactic acid, hence the name of the system. And the problem with this lactic acid is that it causes fatigue and decreases our output. So one of the limiting factors, or the biggest limiting factor of using this system, is this thing called lactic acid and the lactic acid buildup. So again, a flow chart and a cycle, ATP, ADP production. We received 2 ATP molecules from this process this time, whereas the ATP only received 1. What's happening here is we're burning our glycogen, so we're breaking down our glycogen for energy production. This is what's happening as our energy production. Now what happens is, once we break down this glycogen for energy, it turns into this thing called pyruvic acid. Now this is a very important step. So from here, if there's still no oxygen present, which there isn't, we're using the lactate system, it's only lasting between 20 to 90 seconds worth. If there's no oxygen present and we get this thing called pyruvic acid, what happens is we don't have enough oxygen to break this pyruvic acid back down, so what we get is a byproduct of lactic acid. We'll talk about in a minute what happens if you do have oxygen present at this step. So going on with the lactic acid system, provides short-term energy. It's dominant in activities ranging from 20 to 90 seconds of maximal intensity activity. So what's happening here, it involves a series of chemical reactions that break down glycogen into pyruvic acid, producing enough energy to resynthesize 2 ATP molecules. But however, it's important to note that without sufficient oxygen, pyruvic acid converts into the byproduct called lactic acid, which is the thing that causes muscle fatigue as it accumulates. Lactic acid, as well as the production of hydrogen ions, which we'll cover off when you guys go through to Year 12 PE. The last system we're going to look at is the aerobic system, or the oxygen system. Now, the 2 terms I want you guys to learn here are the aerobic glycolysis system. So aerobic meaning with oxygen, glycolysis, you saw that before, the breaking down of glycogen. Now the difference here is with this system is because we've got enough oxygen present, we can actually break down fats. So when we're breaking down fats in this system, it's still aerobic, the use of oxygen, but lipolysis means that we're breaking down of lipids. Lipids is another term for fats. So aerobic lipolysis, breaking down of fats with oxygen, aerobic glycolysis, breaking down of glycogen with oxygen. So it's the main energy system we use in activities ranging from 2 minutes plus. So if you think about it, very rarely can you hold your breath for longer than 2 minutes. That's the best way to work out, can you use this system. After 2 minutes, you're going to start to need to breathe again. The waste products of this system are carbon dioxide and water. So carbon dioxide in high levels is toxic, but water definitely not. So non-toxic waste products, we can expel carbon dioxide pretty easily. So it's a pretty efficient system to use for a long period of time. So like I said before, we burn fats, but it takes longer as a fuel source, mainly because of the fat molecule being a larger molecule and requiring more oxygen to break it down. So we'll go over steady state in a minute, but it can take 3 to 5 minutes to reach a steady state. So when we say steady state, we're meaning where oxygen consumption is matching the oxygen demands activity. We're going to talk about that later on. So important to note here that the aerobic system produces no fatiguing byproducts, but after continuous exercise of 1 to 2 hours or more, there's going to be a likely depletion of our muscle and glycogen stores. Therefore, we're going to need to start breaking down fats as a fuel source. And it's also important to note that it's going to roughly take between 24 hours and 48 hours for the body to replenish these glycogen stores that you lost, even after a high carbohydrate diet. That's where we'll leave it off for this section of the video. Tune in for part 3.